Hello, Georgi Romanic here. Today we are going to talk about dot product between two vectors. Together with vector addition that I discussed in one of my previous videos, dot product is the most common operation between vectors that we use in atmospheric sciences, physics and engineering too. Therefore, in order to study and properly understand these fields, it is necessary to know dot product. Fortunately for you, if you do not know it, after today's video you will. So let's go and check and see how to perform dot product operation between two vectors. Let's say I have two vectors, vector A and here vector B. Dot product A dot B is defined as intensity of A times intensity of B times the cosine of the angle from A to B, and I will call it angle theta. This is angle theta. Immediately we have the first trick over here, because if you know too much mathematics or physics, you might say, but why not measuring angle like this in the other direction? Why are you measuring this smaller angle? And the answer is that this is the definition of the dot product. People agreed that the angle will always be measured as the smallest angle between A and B. Now you might say further, but what if these two vectors are 180 degrees? In other words, if A was like this. Well, then it doesn't really matter if both this direction and this direction are the same, and cosine of 180 degrees is equal to the cosine of minus 180 degrees, and that's minus 1. So in this special case, it really doesn't matter what direction you choose. What are some of the characteristics of dot product? Notice that the result of dot product is scalar. That scalar can be positive or negative number. The units will be the product of the units of vectors A and B. Let's see dot product in Cartesian coordinates. Here I have right-handed Cartesian coordinate system with axis x, y, z. Here are unit vectors I, j, k that I talked about extensively in my previous videos. We see immediately that I dot I is 1. Why is it 1? Because it would be intensity of I times intensity of I, and that's 1, times the cosine of 0, but cosine of 0 is 1, and therefore result is 1. Similarly, j dot j is 1, and also k dot k is also 1. Notice that I dot j, however, is 0 for the same argument, but the cosine of 90 degrees is 0, and therefore this is 0. Also, I dot k is 0, k dot j is 0. In other words, dot product between different unit vectors is 0, and that also means, in a mathematical technical way, that these vectors are independent. Another way to perform dot product between two vectors is through the components, and I will write that here. If we have vector A and vector B, so here is vector A, here is vector B, we know we can decompose them into components, and that's what I did in my previous video, so I'm not going to do it here, but you know, this would be component of vector B along the y direction, here would be along the z direction. The same can be done for vector A. So this is vector A, this is vector B. If we have components, then A dot B is product of these components, namely, that would be AXI plus AYJ plus AZK dot BXI plus BYJ and plus BZK. I hope you can see this end over here. Now, how do I multiply term by term? You know how to multiply these things. So, for example, I take this one, I multiply with bx. I dot I will be 1. So, this will end up being ax bx. Then I multiply this one with this term, but I dot j is 0, so this one doesn't exist. Then I multiply this with the k term over here, but I dot k is 0, so it doesn't exist. So plus, I will do the same here. And hopefully you can see that the only terms that survive is the same terms, j, j, k, k in this case. So it would be a y, b, y plus a, z, b, z. And this is how we perform dot product between vectors if we have components. But notice something special now. And that special is that we can combine this method with this method to actually find the angle between vectors if we do not know the angle but we know components. Namely, I will combine this and this over here, and I will write it here. We can see that AB cosine theta is equal this over here. AX BX plus AY BY plus AZ BZ. From here I can write that cosine theta, which is angle between these two vectors, is equal AX BX plus AY BY plus AZ BZ divided by A times B, where A and B are the intensity of these vectors. Of course, we get them through Pythagoras theorem. For example, intensity of A would be square root AX squared plus AY squared plus AZ squared. And this, so this, sorry for my messy writing, this is AY. If you want to be fancy and show off in disco clubs, you can always write this as A dot B divided by AB. We can also see from this argument over here that dot product is related to projection of vector A on vector B. What do I mean by that? Let me plot this again. Here is vector A, here is vector B. If I make a projection of vector A, how do I make projection? I start from B and I go to head of vector A, where this is right angle. Then we say that this over here is A subscript B, which means that is projection of vector A on vector B, and that would be A cosine angle theta. This would be A normal, because it is the component of vector A normal to the vector B, and that would be, of course, A sine theta. So a dot product between A and B finds how much of vector A is in the same direction as B and then multiplies that with the magnitude of B. Because look, this much of A is in the direction of B, and then I multiply that with B, and look, this exactly equal to what we had here. So this is another way to look at the dot product between vectors A and B. From here, I am not going now to waste more time, but you can clearly see that A dot B is equal to B dot A. What I would like to mention though, that vectors are not fixed in space. So if somebody gives you vector A here and vector, I don't know, B over here and asks you to find dot product, you cannot say I can't do it because they are not touching each other. What you need to do, you have vector A, I just plotted it here, you move vector B, and now you find dot product between these two. In other words, we can move vectors in space. Somebody perhaps can ask you, but what if you have triple dot product? A dot B dot C. Well, the person that asks you that indeed is not very good at mathematics, because this statement is meaningless. Why? Well, let's A dot B is something that will be scalar. Let's call it, I don't know, M. But that M is not vector, so I cannot, we know from my video on vectors and scalars, I cannot have scalar product between scalar and vector C in this case. This doesn't mean anything. What we can have is some scalar M multiplying C, but this is multiplying, not dot product. So it is important to distinguish between these. Dot product is one of the most important operations in vector calculus. I hope after watching this video you understand how to properly carry out this mathematical operation. Until next video, goodbye.